Hello students. Uh, Today I am going to discuss about some standard signals. We have already discussed some of the standard signals. Before going to discuss standard signals, remaining standard signals, I will revise what are all the things we have discussed in our previous classes, right? First, we have discussed what is signal and different types of signals such as one-dimensional signal, two-dimensional signal, three-dimensional signals with examples. Then majorly signal is classified as, right, continuous time signal and discrete time signal. And also we have discussed how to convert continuous time signal to discrete time signal. So even we have solved problems related to how to convert continuous time signal to discrete time signal. Thereafter, we have discussed some standard signals such as ramp signal and unit impulse signals, unit step function with respect to both continuous and discrete time signal, right? So, and also I have discussed rectangular pulse functions. Before that we have discussed the properties of unit impulse function, right? We have discussed 3 to 4 properties. Please try to memorize those properties are very important to solve the problems. Okay, so thereafter we have discussed rectangular pulse function, right? Then triangular pulse function. Okay, so now I will discuss again I will discuss triangular pulse function. Okay, then we will see some more signals. Okay, so mathematical representation as well as graphical representation. Okay, we'll see one by one. So triangular pulse function, right? So how we are representing, the name itself indicates the triangular, right? So we are representing like a mountain, right? So initially, so it is, we are using this magnitude is the triangular pulse magnitude is 1, right? From this magnitude, we are going to define the triangular pulse function. From this magnitude, that constant magnitude, right, or DC signal, from this DC signal, right, or constant, that is the correct word, that constant, from this constant magnitude. So we are defining the triangular pulse function, right? So this is constant magnitude 1, right? We are subtracting this t is a ramp signal with the scaling factor a, right? So that ramp signal is scaled by 1 divided by a, right? 1 divided by a, right? This is a t is represented within the modulus, right? Then if the value, if the time, the time is either positive or negative time, then the output should be positive, right? So that is the indication of modulus, right? The value of t is either positive or negative, the output is should be positive. Okay, so if the modulus of t is less than or equal to a, right? If the modulus of t is less than, right, or equal to a, so if equal to a, then only the the magnitude of triangular pulse function is 1 minus t divided by a. If the if the time function is greater than a, so if the time function is greater than a, I mean like this, if the time function is greater than a, then the magnitude of triangular function is 0, right? So this is the mathematical representation of triangular function. This is the graphical representation of triangular function. Okay, so similarly signum function. Okay, So signum function we are representing mathematically like this. So this is graphical representation of signum function. Okay, so we are symbolically represented as, right, sgn means signum function of t, right? When t is greater than 0, when the t is the time. Okay, it is represented in the x-axis, right? This one is the magnitude which is represented in the y-axis, right? This is magnitude, this is the time period. Okay, so when t is greater than 0, I mean if t is greater than 0 means if the t value is 1, 2, 3, right, and so on, right? So when t value is greater than 0, the magnitude of signum function is 1, right? So similarly when the t value is less than 0, if the t value is less than 0 means the value is -1, -2 and -3 and so on, right? Then the magnitude of signum function is -1, which is graphically represented as shown in this figure, right? So what happens when t is equal to 0? When t is equal to 0, right, the signum function magnitude is 0. Okay, so actually um, this function, this graphical representation or the signum function is a, we call this one as a even function, right? So it is not a even function, this is a odd function. Why, ma'am? How we are telling this one as a odd function? We will discuss this even and odd function in detail. Okay, see here, when t is positive, the magnitude is 1, right? When the t value is positive, the magnitude is 1. When t value is negative, right, the magnitude is -1, right? So for example, if the t value is less than 0, I mean if the t value is negative, even if I am getting the signum function is 1, then we call this one as a even function, right? Then that the graphical representation looks like this, right? Even when t is greater than 0 or t is less than 0, right, the magnitude is 1. In this condition, this type of function we call that one as a even function. But here in the signum function, I am getting opposite magnitude, because when the t value is positive, the magnitude of signum function is +1. When the t value is negative, right, the magnitude value is -1, right? So I am getting opposite sign, right? So such type of function we call that one as a odd function, which means the signum function is a odd function. Okay, so uh, we can possible to represent signum function by using unit step function. We will see how to represent the signum function, okay, by using unit step function. Okay, this is the representation of signum function using a unit step function, right? Signum function can be represented as -1 plus 2 times of u of t, right? You know very well how the mathematical representation of u of t, that is when t is greater than equal to 0, right, the magnitude of u of t is 1, right? The magnitude of u of t is equal to 1. So this is the graphical representation of unit step function, right? So here when t is greater than 0, okay, when t is greater than 0, the u of t is 1, right? So 2 into 1 is 2. 2 minus 1 is equal to plus 1, right? So when t is greater than 0, the signum function, the magnitude of signum function is plus 1, right? So it's satisfied. So it's satisfied it satisfied this condition, right? So now we have to prove this one using a unit step function. Okay, so when t is less than 0, the unit step function is, we know that very well. So when t is less than 0, the magnitude of unit step function is 0, right? So the magnitude of unit step function is 0 when t is less than 0. So, so when t is less than 0, in this condition, u of t is equal to 0, right? So u of t is equal to 0, right? So 2 is multiplied with 0, so we will get the signum function magnitude is -1. So this condition is also satisfied, right? So when t is equal to 0, what happens in the signum function? So when the t is equal to 0, the magnitude of signum function is also 0. Okay. So we will see the next function is sinc function, right? We call this one as a even function. How we are calling, ma'am, this sinc function as a even function? As I discussed before, right? So when t is greater than 0, right? So the magnitude is here in this condition, it is gradually decreasing, right? For even here, when t is less than 0, here also the magnitude is decreasing, but the magnitude of both the in both the condition, that is when t is greater than 0 or when t is less than 0, the magnitude is positive. That one is very, very important, right? So that's why we are calling this one as even function. The, for example, if the function I am not getting positive, I am getting negative value, means so this one is not a even function, this is a odd function. Okay, so now this one is a even function. Sinc function is a even function. Okay, how we are representing mathematically? Sinc, S-I-N-C, sinc, C, okay, S-I-N-C, sinc function of t is equal to sine t divided by t. This t, the time is lies between minus infinity to infinity. In the graphical representation, it shows that when t is is equal to infinity, or when t is increases gradually, the amplitude of the signal decreases. When t is equal to infinity, right? So the amplitude is almost 0. Similarly, when t is when t is less than 0, I mean -1, -2, -3, gradually the amplitude of the sinc function is gradually decreases, right? So when t is minus infinity, right? So then the amplitude of the signal is 0, right? So here the sinc function, right? The sinc function, it is an oscillating, right? The sinc function is oscillates with 2 pi, right? With 2 pi. 2 pi means 360 degree, right? 2 into pi is a 180 degree. It is a 360 degree. So oscillates with the period 2 pi, right? So, so period is time, right? Here the period is time, so we can't tell that one as a degree, right? So here t is the period, so t is equal to 2 pi. We can also represent time with respect to pi, okay? 1 pi, 2 pi, 3 pi, 4 pi, and so on. Okay, so and that t is lies between minus pi to pi, then the total time period is 2 pi. Okay, so it is oscillates with the period 2 pi, right? So as I said before, as the amplitude of the sinc function, right, it is gradually decreasing when t value is increases, right? Similarly, and before that, so the amplitude is becomes 0. This amplitude becomes 0, so when t reaches n pi, right? When t reaches n pi, here where n, the n value is plus or minus 1, plus or minus 2, and so on up to infinity. So the n value varies from 1 to infinity. Okay, as I said before. So similarly, so the negative value, the when t is less than 0, the amplitude is also gradually decreases when t value is lies between minus 1 to minus infinity. When t value is minus infinity, almost the amplitude, this is the amplitude, right? This is amplitude. The amplitude of the signal becomes 0. Okay, so next one is Gaussian function, right? So these functions we are using in different ways, right, as a Gaussian noise in our signal, right? There are two types of noise, white noise and Gaussian noise. So might be you will study in your communication. Okay, so and also this Gaussian noise will also come in digital image processing. Okay, so now we will study just that representation, mathematical representation and graphical representation. Okay, so mainly it is used in the probability theory. I am not going in detail about this one. Just I will discuss about the mathematical representation and the graphical representation. So we are symbolically represent the Gaussian function as g subscript of a function of t is equal to e to the power of minus at square. That t is lies between minus infinity to plus infinity, right? This is the mathematical representation of Gaussian function, right? So this one is the graphical representation of Gaussian function. Okay, so the x-axis is the time, right? So the unit is second. The y-axis is the magnitude of the Gaussian function. Okay, so the maximum value of Gaussian function is 1, right? That the magnitude of Gaussian functions lies between 0 to 1. So when t value is 0, right? So when t value is 0, right, the magnitude of Gaussian function is maximum, right? When the t value is positively increases, right? So when t is greater than 0, right? So when the t values increases, correspondingly the magnitude of Gaussian function decreases. At certain time period, the magnitude becomes 0. So similarly, so when t value is less than 0, which means the value of t is negative, right? So when the t value, the negative value of t is increases, right? So the magnitude is also correspondingly decreases. At certain time period, the magnitude of Gaussian function becomes 0. It looks like a bell-shaped curve or inverted parabolic curve, right? The parabolic curve we are representing like this. It is a inverted parabolic curve, right? This is an inverted parabolic curve. We can also call this one as bell-shaped curve. Okay. So next, so we will discuss about sinusoidal signal. You know very well how to represent the sinusoidal signal in mathematical way, right? So x of t is equal to a is the amplitude, omega is the angular frequency. We are representing, the unit is radian per second, right? So pi is the phase, right? Phase angle we are representing in radian. Okay, phase angle we are representing in radian. Amplitude, the we are representing in, if it is voltage means unit is volt, if it is current it is ampere, right? So this is an angular frequency, right? We are represent, the unit is radian per second. Okay, radian per second, that this is a pi is the phase angle, the unit is radian. So we will take one example. So the amplitude is 1, pi is the phase angle in radian, right? So then t is 2 pi by omega. How we are getting this one, the equation of t? T is the unit of t is second, right? T is a fundamental time period, right? So fundamental time period. How we got this equation means, we know that the relationship between the frequency and the angular frequency, right? So omega is equal to 2 pi f, right? So f is the reciprocal of fundamental time period. Just I have substituted this one here. So instead of f, I have used 1 by t. If I am rearranging this equation, I will get this equation. Okay. So we are representing t value with respect to angular frequency. So t is equal to 2 pi by omega. Okay. This is the amplitude. Okay. Amplitude is 1. Sorry. Amplitude is 1 here. This is the amplitude minus 1, right? Then where is that phase angle? So we are representing phase angle here in degree, right? So degree are normally we are used to represent in degree, right? So for example, if it is 180, pi is 180, right? 180 divided by 3 means 3 6 18, right? So it is a 60 degree, right? So usually the if we are representing the one cycle in 180 degree means, right, this is a sinusoidal signal. If we are representing in a 180 degree cycle, right? So 180 degree means this one is a 0 degree, right? This one is a 45 degree, right? So this one is the 90 degree. Okay, this one is 135 degree. Okay, this one is 135 degree, and this point is 180 degree. This is the 180 degree cycle. Okay, this is very very important. So we will use these things in our EC2. Okay, while studying EC2, even you have studied this one in your circuit analysis. For example, if we are representing a one cycle in a 360 degree means, then that angle we are the angle is first as like 180 degree cycle. We'll also get first one is a 0 degree, right? This one is a 90 degree, right? So this one is a 180 degree. Okay, this one is this one is 180 degree. This one is 270. Okay, so finally this one is a 360 degree. Okay, this is the one side a 360 degree cycle. So we are representing one cycle in a 360 degree. This is the one cycle we are representing in a 180 degree cycle. Okay, so if we are taking 180 degree means, usually we will use 360 degrees, okay, to represent the sinusoidal signal, right? So if it is 90 degree, if it is here, it will comes 90 degree. 60 degree means it will comes here, right? So it will comes here. Okay, so normally, so we can also represent that cycle like this if it is in degree, right? So we are representing like this. If it is 90 degree means, how we can represent that cycle? So the 90 degree comes here, right? So like this, it will goes like this. So the one cycle means you have to take this point to this point. Okay, so similarly, here we are representing the sinusoidal signal for this specification. Okay, then after, right? So we will see the next function is a real exponential signal. Okay, so real exponential signal. So how we are representing real exponential? What is the difference between the complex exponential signal and real exponential signal? We will see that. Okay, first we will understand the real exponential signal. I mean, in the exponential signal we don't have any imaginary part, right? So usually we will represent the complex exponential signal using this, right? X of t is equal to e to the power of st. So we know that s is the frequency domain representation, right? So s is equal to sigma plus j omega, right? This is the imaginary part of the signal, imaginary part of the s, right? So this is the representation of complex exponential signal, right? This is the representation of real exponential signal. Here the imaginary part does not come into the picture. Okay, so we will see only the real part of the exponential signal. So we will discuss this with respect to the mathematical representation and also graphical representation. Okay, first, so how we are representing this real exponential signal in mathematically? So x of t is equal to a into e to the power of at, right? So this is the graphical mathematical representation of exponential signal, right? So we will see one by one. Okay, what happens if the value of a is equal to 0, right? When a is greater than 0 and when a is less than 0. Okay, so we know that if a is equal to 0 means the exponential of 0 is equal to 1, right? So we know very well e to the power of 0 is equal to 1. So the amplitude of x of t is a. So how we are representing that one in in graphical way? So we are representing like this, right? When t is equal to 0, the amplitude is 1, right? Our amplitude is a. So what happens when the a value is greater than 0? Greater than 0 means if the a value is positive, what happens? Just apply the value of a as a -1. Okay, just find out the value of x of t, right? So and a value is, sorry. So if the a value is positive, right, it is not negative. If the a value is positive, right, first substitute the value of a as a -1, -2, -3 and so on. Then at t is equal to 0, find out the value of x of t, right? And also um, 1 second students, 1 second. Sorry students, so just initially you have to assume, so a value as a positive. I mean, if a is greater than 0, for example, if a is positive value, right? So change the value of t, right? So I mean, vary the value of t, right? So for example, just substitute the value of t as a -4, right? Not a, that one is t. Just fix the value of a first as a positive value +1 and then vary the value of t, right? Just substitute the value of -4, -3, -2, -1, 0, +1, +2, +3. So if we are increasing the value of t, so gradually the amplitude of the exponential signal, right, or magnitude of the exponential signal increases. So when a is greater than 0, I mean when the positive value, when the value of a is increases. What happens if the value of a is decreases, right? Which means when the a value is negative, right, what happens? So it is exponentially decreases. How we can determine the value of exponential signal? So when the a value is negative, how the exponential signal, the magnitude of exponential signal is gradually decreasing? Just substitute the value of t from negative to positive, right? From negative to positive. Okay, as we did in when a is greater than 0, right? Just substitute -4, right? So here the a value is -1, right? So substitute -4, it becomes +4, right? See, in +4, in the -1 value, right? So it is higher value, right? We'll get the positive value, right? The magnitude is positive value. So as the t values goes on increases, I mean -1, 0, 1, 2, 3. So the amplitude of the exponential signal is gradually decreases. Just substitute from -4 to +4. Just verify whether I have said correct or not. Okay. Then, so complex exponential signal, right? So as I said before, right? So this is the S domain function, right? Frequency, we are converting time domain signal to frequency domain. So right, by using Laplace transform, right? So right now it is not required. Just we know, just please understand. So the complex exponential representation, right, in the S form, in the S domain, right? So S is we are representing in real part and imaginary part. This is sigma, this is an omega, right? Capital omega, this is sigma, this one is the capital omega. This is the imaginary part of the complex signal of S, right? So just substitute the value of S, right? So S is equal to sigma plus j omega into t, right? Just by using a exponential property. So if it is addition means it becomes multiplication, right? E to the power of sigma t into, right? Into e to the power of j omega t. You know very well. So right, this is the property of exponential function. Okay, then by using a Euler's identity, we know that, so e to the power of j theta, right? E to the power of j theta, right? Cos theta plus j sin theta. You know that this equation very well, right? We are using this same equation in order to represent e to the power of e to the power of sigma plus j omega t, right? So we are writing this equation like this, right? So by using Euler's identity, by using this condition, so we are representing this one as a cos theta plus j sin theta. See here, e to the power of j omega t, we know that cos omega t plus j sin omega t. Just substitute this equation 2 in equation 1. Okay, then so we will get this equation, right? Now we will analyze this equation by substituting different values for sigma and omega. Okay, so see here, first condition. So if sigma is equal to 0, sigma e to the power of 0 is equal to 1, right? Sigma is equal to 0 and capital omega is equal to 0. What happens? So substitute this sigma is equal to 0 and capital omega is equal to 0 in this equation. What happens? So cos of 0 is equal to 1, right? Sin of 0 is equal to 0. Okay, so e to the power of 0 is equal to, because sigma is equal to 0, e to the power of 0 is equal to 1. So x of t is equal to 1, right? It is a pure DC signal, right? So we will represent graphically like this, right? So second condition is when sigma is equal to 0, then S is equal to sigma, right? So just substitute this one, right? In this equation, right? S is equal to sigma plus j omega. Omega is equal to 0. We will get S is equal to sigma, right? S is equal to sigma. Okay, right? Afterwards, and x of t becomes, right? So x of t becomes, what happens? Just substitute here itself, nothing, there is no problem, right? So substitute. So sigma is equal to 0, cos of 0 is equal to 1, sin of 0 is equal to 0, right? Then s is equal to, sigma, right? We will get this equation, right? We will get this equation, a to the power of sigma t, right? Because s is equal to sigma, right? So we will get this equation, e to the power of sigma t. Okay, then if sigma is less than 0, if sigma is less than 0, sigma is less than 0 means if it is negative value, what happens? What happens if the sigma is negative value means what happens? So x of d decays exponentially. We will see that. So if it is s is minus sigma, when sigma is less than 0, what happens? This is sigma, right? When sigma is less than 0, what happens? So it is exponentially decreases, right? So what happens if the sigma is greater than 0? If sigma is greater than 0 means it is exponentially increases. Okay. So similarly, so I have used in the if s is plus or minus j omega, right? If then if s sigma s is equal to sigma, right? So plus or minus j omega in this condition, right? When real part is 0, right? Sigma is 0. When s is equal to plus or minus j omega, right? So in this condition, right? In this condition, right? So in this condition, what happens when sigma is equal to 0, when real part is equal to 0, when s is equal to plus or minus j omega, what happens? So how we can represent e to the power of plus or minus j omega? Cos omega plus j sin omega. If it is minus, cos omega minus j sin omega, right? So we are representing as a sinusoidal with a constant amplitude, right? So constant amplitude. This one is a positive side of cosine and sinusoidal signal. This is the negative side of cosine and sinusoidal signal. Okay, ba? This one. This one. Okay, ba? With constant amplitude. Okay, ba? So then, so what happens when s is equal to sigma plus or minus j omega when sigma is less than 0? I mean, the sigma value is negative. What happens? That sine and cosine function, right? So it is exponentially decreases here, right? In the sine and cosine functions, what happens? That amplitude of the sinusoidal function is exponentially decreases. Similarly, when summation sigma, sorry, not summation, sigma, when sigma is greater than 0, what happens? It is exponentially, the amplitude of sinusoidal signal is exponentially increases, right? So we will see the sum of the problems. Okay. So I hope you will understand the basic elementary signals. Thank you very much.